Hello, guys. Today I wanted to give you a quick walkthrough on the assignment that we have done for deep learning. So, which is neural networks with Keras. So, this is our part one. So, we have given a couple of parts from A to L. So, these are all the various data augmentation and generalization techniques. So, which we have done in TensorFlow. So first, I wanted to give you a detailed explanation of what is what and on. So when it comes to L1 and L2 regularization, so what are basically L1 and L2 regularization? So when it comes to this question, so basically L1 and L2 are regularization techniques that help prevent overfitting in your models by adding a penalty on the magnitude of future weights. So L1 regularization promotes sparsity, making it is very useful when you want to reduce the number of features of a particular data set. So here we have generated a synthetic data. So based on this data set, we are performing L1 and L2 regularization. So L2 regularization, on the other hand, tends to spread the error among all the weights and is generally good for reducing the model complexity and overfitting. So in TensorFlow, these can be easily added to the layers using kernel regularization parameter. So here we can see we have used kernel regularization. So let's go a quick walkthrough. First, we have installed all the necessary libraries. Let's run this, and then we have created a synthetic data, and then step two comes to the creation of model building. So let's create a model using parameter, kernel regularizer parameter. So and then we have implemented training part of this model that we just created. Let's run this. Okay, so we have given like 20 epochs, and we can see the loss, how much loss we have got. Let's evaluate the model, and then let's see the results in a plot diagram. Here we can see the validation loss and training loss while performing testing and training of our model. Here is our first part, L1 and L2 regularization. So after that, when it comes to the dropout part, so dropout is a form of regularization, so which is also a form of regularization used to prevent overfitting. So it works by random setting a fraction of inputs units to zero at each update during training time, which helps to make the model robust as it can't rely on a single feature. So TensorFlow implements a dropout through the dropout layer. You can see the dropout layer here we have used. So callback, so which can be added to neural networks. So let's see the quick overview of how this model works. First, we have installed necessary libraries required for dropout, and then we have created a model using dropout layer, and then optimize the Adam, and then we have implemented mean square error here. Let's train this model with 20 epochs and with validation zero point 0.2. Okay, successfully executed, and we can see the training loss here we got. And then let's see the results by plotting the model using matplotlib. And then when it comes to the early stopping. So early stopping is also a form of regularization used to avoid overfitting by halting the training process if a monitored metric has stopped improving. So TensorFlow supports each early stopping through the early stopping callback, which can be monitored metrics like validation loss or validation accuracy and halting training accordingly. So first we have gone through the setup of early stopping layer. So let's run this, and then we have defined a model, which leads to building the model using relay activation functions, and also using the optimizer atom. So let's train this model like we did for dropout layer, and then let's see the evaluation results by plotting the graph. Here you can see the model training loss and then validation loss. So what this graph basically states that the point at which training was stopped, and you should see a stabilization increases. You can see the stabilization increases or increase in validation loss prior to stopping if early stopping was triggered effectively. That that is basically about early stopping. So moving on to the Monte Carlo, which is also called MC dropout. So what is basically a Monte Carlo dropout is that it is an extension of the dropout technique that we have seen prior, used at interference time to provide a better estimate of model's uncertainty. Unlike standard dropout used only during training, Monte Carlo dropout enables dropout during inference, averaging predictions over multiple stochastic forward passes. So this is useful in critical applications like medical diagnosis and all. So we have installed necessary libraries, and then when we imported a dropout layer, and then we proceeded to build the model, Monte Carlo model, using activation functions like ReLU, and then optimizer atom like we did before. And then we proceeded to train the model using 20 epochs. And we see how this model resulted in the loss and validation loss. And then we have implemented Monte Carlo dropout for predictions. Let's see how it goes. And we see how these results are plotted. Like we can see the uncertainty of the model. So this plot will show the predictions along the uncertainties as error bars, demonstrating the various variance in predictions due to stochastic nature of dropout during interference. So let's move on to the next part, which is various initializations and when to use what. So when it comes to this part, so weight initialization can significantly affect the speed of convergence in training deep neural networks. So TensorFlow provides several initializers like zeros, ones, and then random normal, random uniform, Glorart normal, and He normal. So by using all these initializers, let's see how the model will perform and how it will uh, evaluate results and all. Let's run the model using defining all different initializers: zeros, ones, random normal, random uniform. got normal and he normal. Okay, uh, so we have created a model. So now we train this model. Let's see how it goes. Here you can see we can observe which model, like which initializer resulted the loss. You can see the model, particular model of the training loss and then validation loss. Let's see by plotting the graphs. Here you can see there are there are the plots of a particular initializers. So this is the plot for zero initialization. So validation loss and then epochs. And this is the plot for one initializer. You can see the drastic loss when improving the epochs. So the random normal initializers drastically increased when we increase the epochs proportionally. So here we can see the random uniform initializer and then load normal initializer, which also perform the same as random uniform initializer. Validation loss with he normal initialization. So these are all the plots display the validation loss across epochs of each initializer, showing which initializer might be more effective or efficient in training under these conditions. So moving on to the next one, batch normalization. So batch normalization, which is also a technique that stabilizes and accelerates the training process by normalizing the inputs of each layer so that they have mean output activation of 0 and standard deviation of 1. So here we have gone through the building of the model by using normalization. So we have imported normalization here, and then we have used activation function ReLU from the TensorFlow Keras layers. Let's run this model using optimizer Adam. So we have successfully built the model. Now we'll train the model. Let's see how it goes. Here you can see this batch normalization almost significantly gave us the less loss when compared to the other uh, data augmentation techniques. And then we've evaluated the model here. Let's see by plotting the graphs of this model. So here is the graph for a model loss with batch normalization. So this graph will show you how the loss progresses over each epochs and can help demonstrate if batch normalization helps in achieving lower validation loss or in faster convergence compared to the models without it. So that is it for batch normalization. So after that, we have also implemented a custom dropout, custom and regularization. It is not custom; it's custom. Okay, perfect. So what is custom dropout in customer regularization? So in TensorFlow allows you to create a custom dropout and regularization techniques by subclassing layer or regularizer classes. So this is useful when standard models are not sufficient and you need to behavior specific to your application, such as a spatial dropout or a novel form of regularization. So this might be necessary if you have a unique architecture, or if you're working with data that has a particular characteristics. So let's proceed with create a custom dropout layer here. You have successfully created a custom dropout layer. Then we will create a custom regularization function here. Let's using these layers, we'll create a model using L1 L2 regularizer here. And then we have used activation function relu here. Let's proceed with training the model. Again, we have taken 20 epochs, which is sufficient for every model, almost sufficient to give our desired loss. Here we can see we have got the loss by using custom dropout and regularization technique, which is 1.70, which is pretty good. So let's plot the graph by using matplotlib. Here you can see this graph. The custom dropout layer and L1 L2 regularizer are simple examples. You may need to adapt them based on the specifics of your dataset or model architecture. Let's see the map of this without custom dropout or regularization. This is the custom dropout regularization. This is without custom dropout regularization, how the function, how the model performing. Okay, moving on to the next part, using callbacks and tensor board. So this part involves using callbacks, including the early stopping callback we have covered earlier, which is part C, and monitoring training progress with TensorBoard. So which is a powerful tool provided by TensorFlow to visualize various metrics during the training process of a machine learning model. So first we have set it up TensorBoard. Let's run this. Already loaded because I've already run this cell while I'm performing this assignment. And then we have built a model using activation relay function. Next, we'll proceed with training the model using callbacks. We have we are calling back the early stopping data augmentation technique that we used earlier, and then we have given 50 epochs here to train the model. Let's see the results in TensorBoard. Up to now, we are visualizing all the graphs in using Matplotlib, right? So for this, we will visualize all the metrics and then all the validation loss and training part in TensorBoard, how the model is performing. Let's see. Let's run this cell. You will see a board which is representing all the graphs here. Here you can see the board is loading. You can see all the metrics. We can basically monitor all the performance of the model, like the training part, and then how well the model is performing, and then we can easily observe what is going on with our model. Here you can see the tensor board also provides other visualizations such as graphs of your model, histograms of weight, bias, distributions, and more. By analyzing the plots and data in tensor board, you can make informed decisions about stopping training, adjusting hyperparameters, and experimenting with different model architectures. So moving on to the next part, which is using Keras tuner. So what is exactly the Keras tuner? So Keras tuner is an easy to use, scalable hyperparameter tuning framework that solves the pain of manually searching for the best hyperparameters for your model. So it supports various tuning strategies like random search, hyperband, and then Bayesian optimization. So let's install this Keras tuner here, and then we have imported necessary libraries, and then we have defined the model here, and then we have proceeded with initializing the tuner, random search. Here we will use the random search tuner here. Let's prepare the model for training and then validation. Let's see which model is performing the best. So let's see the mean square error here, and then moving on to the next part, using Keras CV data augmentation. So in this part, Keras CV provides tools for data augmentation directly in model layers, which allows for GPU accelerated augmentation. So this is efficient and can be easily integrated into your data pipeline by increasing the diversity of data available for training without actually collecting new data. So Keras provides a simple API for data augmentation using image data generator. Here is how we can implement this model. So let's install all the necessary libraries and then imports. Let's load and pre-process the data. Here we've used a Cipher 10 dataset while we are dealing with the data augmentation dataset. So let's define the data augmentation, and then defining the CNN model, convolutional neural networks, and then we have proceeded with training the model by implementing 10 epochs. I think it might take some time to execute all the epochs. Let's wait for the moment, and then we will proceed with evaluating the model. It might gonna say take some time. Yeah, we'll wait patiently. So right now it is executing 8 epoch of the total of 10 epochs. Let's see after this training how the model is performing by evaluating the model. So let's move on to the second part, which is advanced Keras deep learning constructs and concepts. So here is our assignment description that we need to do for part two. It consists of like several subparts, which is user custom learning rate scheduler and all the way to custom training loop. So I'll give you a quick walkthrough of every other part that is described here. So let's move on to the first part, custom learning rate scheduler. First, we'll go ahead and set up the environment. So let's install the TensorFlow. So before that, what is custom learning rate scheduler? So so we all start by implementing a custom learning rate scheduler, specifically cyclical learning rate scheduler. This scheduler varies the learning rate between a lower and upper bound, which can help in avoiding local minima and speed up the conversions. So we'll see how to integrate this with Keras callback system. So install all the necessary libraries and then importing, and then we'll create a synthetic data. Let's run these two, and then we will move on to the next step, which is defining the custom learning rate scheduler. So using Keras callbacks, and then we proceed to build a model, and then like we did before for the first part, as usual, like train the model using, like you can use any number of epochs that you want, but we limit the epochs to 25, which reduce our time. Then let's proceed to plot the graph. So that is it about first part, which is custom learning rate scheduler. Next we move on to the next sub part, which is using custom dropout. So we will implement a Monte Carlo, which is a MC dropout variant here, which can be used to estimate model uncertainty, and it is more effectively by keeping the dropout active at inference time. So we'll defining the Monte Carlo alpha dropout layer here. Let's run this, and then we'll build a simple model using Monte Carlo alpha dropout. Let's train the model here using 100 epochs this time, which is you can see the it's training the model, which is very fast. Let's evaluate the model. and plotting the graphs using matplotlib. Here you can see the actual data and predictions of the data, which we used a custom dropout layer uh, using Monte Carlo dropout layer. Next, we move on to the next subpart, custom normalization. So in this section, we'll create a custom normalization technique where we constrain the weights of a dense layer using maximum norm. This is useful for controlling or fitting by imposing an upper limit of the size of the weights. So let's move on to define the normalization layer. Here we've used a max norm dense layer. Let's proceed to run this. And then we proceed to build the model using max norm dense layer. And then we proceed to train the model using 100 epochs now. And then we'll also calculating the mean square error. So you can see the error, how much error we've got. Let's run this to print the mean square error here, and then we'll plot the results of our model. Moving on to the next step, which is using TensorBoard integration. So again, as we discussed in our first part, TensorBoard is a powerful tool that enables you to visualize dynamic graphs of your training and then test metrics, as well as histograms of weights, biases, and other parameters. So we'll first install the necessary libraries and then imports TensorBoard here, and then we'll set up the TensorBoard logging here. It will launch the TensorBoard. Here you can see the TensorBoard, which is not have any type of data loaded to this model. So we'll load the model, and then we'll train the model. So after training the model, uh, the data is loaded. The trained data is loaded to the model. Then we can see the metrics and then the results in the tensor model. Like we can monitor what is going on with the model. Here you can see the performance of the model, training histograms. Then we also have a dense layer performance here. We can see the performance of the dense layer, and then how much epochs for each epoch, the train and validation loss here. In this way, we can monitor all the performance of our model using TensorBoard. So moving on to the next step, which is custom loss function. Here we have used a Huber loss function. So the Huber loss function is less sensitive to outliers, which is errors in data, than this squared error loss. So we will implement it as a custom loss function and apply it to the regression model, and then comparing its performance with traditional loss functions. So first, we have defined a model using Huber loss function, and then we'll compile the model here using sequential SGD optimizer, and then we'll proceed with training part, training the model. It's performing really good. As we can see, the loss values are significantly decreasing each epoch, and then we'll proceed with evaluating the model to know the mean square error of the test set. Here we can see we have observed the mean square error here, and then we'll proceed with saving the model, which we can retrieve again and again from this. Then we'll save the model here. That is it for custom loss function using Huber loss function. So, and then moving on to the next step, custom activation function. So, custom activation function. So, we'll define a leaky relu activation function, even though Keras already has a built-in one. For demonstration purposes, we use a leaky relu here. First, we'll define the leaky relu, and then if define the custom initializer, which is a Glorot initializer here, and then we'll implement element regularizer, and then we'll implement custom constraint here. So bringing them all together and performing a model, and then compiling the model. Now the model is built using all the three, like custom constraint, custom regularizer, and custom initializer. So and we then proceeded with training the model. After after training the model, we'll proceed with evaluating the model. Let's evaluate the model to get the mean square error. Yeah, it is quite good performing. It is performing really well. Let's visualize the weights. Unfortunately, this is not the correct one, but if we used activation functions and then some optimizer, uh, by reducing some optimizer regularization, we can get a pretty good performance. Moving on to the next step, which is custom metrics. So here we have used Huber metric. So just as with this custom loss function we have used, so we will implement Huber loss as a custom metric to monitor model performance during training, providing a robust way to track regression model accuracy. So we then first defining the custom metrics. We have used, as I said, custom metrics as Huber metric. Let's run this model, and then we'll define the Huber function, and then compiling the model, training the model using 100 epochs as of now. If you can increase the epochs, you can observe a good performance of the model. And then it's done, training is done, and then we'll proceed with evaluating the model. So the next part is custom layers. So here we've used a Gaussian noise layer. We'll create a several custom layers to demonstrate how we can extend Keras functionality. So these layers will include an exponential activation layer, a dense layer with some added Gaussian noise, and a custom layer for batch normalization. So first, we define the custom layers, which is Gaussian noise layer, normalization layer, and then using the two layers, we'll create a model, and then we'll proceed with training the model. After training the model, we will evaluate the performance of the model using mean square error. So we then for implementing these graphs, will load the data to the train loss and then validation loss, importing matplotlib libraries. We can see the graphs of the model performance. Yeah. Moving on to the next step, which is custom model. Here we've used a residual block layer as our custom model. So in this part, we will create a model with residual connections. A residual connections skips one or more layers by adding the input of previous layer to the output layer later, which can help the training deeper networks. So first we'll define the residual block layer. Residual block layer is not defined. Okay, we then proceeded with plotting the graphs, adding the second residual block here. Full residual regressor is not defined. I think first we need to define the block layers here. I think I forgot to defining it. I'll perform that step later. Again, next part is custom optimizer. So in Keras, an optimizer is a slightly more complex component to create because it involves creating a class that updates the weights of the network. For demonstration purposes, we'll create a simple stochastic gradient descent optimizer with our momentum, which is a simplified version of one that Keras already provides. Let's define the custom optimizer here, and then evaluating the model. So again, as my other classmates are also getting the same error, so we have talked with our professor regarding this error. So we have worked on this error for a significant time, but we still didn't know where this error is coming from. So we are leaving it as of now. So you can see the error indicates that set hyper method is not available. So it seems there might have been a misunderstanding on how properly implement a custom optimizer. So the Keras API has changed over time, and the process of creating custom optimizer is more complex than what the provided snippet suggests. So moving on to the final step, custom training loop. So first we've defined the model using sequential function, and then we have defined loss function and optimizer. Here we used mean square error as our loss function, and then SGD as our optimizer, and then we have defined the metrics, defined the number of epochs to be trained, loading the data to the training data set and then train data set. We proceeded with building the model and evaluating the model. Yes, and then here you can see TF graphs. Somewhere it is in here. TF gradient tape. You can see the TF gradient tape in this function. I don't know. Yes, TF gradient tape. This one is used for automatic differentiation, computing the gradient of the loss with respect to the inputs. So apply gradients updates the model weights. Metrics are tracked via a mean and the mean absolute error objects. Before running this loop, we need to prepare our trained data set, which should be a TF data set object. Here is an example. So we'll then plot the graphs for loss and then means absolute error. Here you can see the graphs of their respective like loss functions and then mean absolute error. That's all about our part 2.